going to talk about uniform irreducibility. Galois action on the L primary portion of the Boolean threefold to pick up.
Yeah, thanks, Chris, for the introduction. Thanks, Daniel, for putting up all this conference. You already done better than your advisor in organization-wise, and let's hope that this tradition lives. Yeah, unfortunately, I didn't. When I was preparing my talk, I didn't notice it was a p-adic conference. So here, it will be L will be the prime number. So there will be a p, but yeah, it will be mainly L. So everything today stems of discussions and collaborations with Dinakar Ramakrishnan from Caltech. And so the starting point of these discussions was that we were both fascinated by Mazur's famous paper on the Eisenstein ideal, which will be like 50th anniversary next year of the appearance of this paper. And we were wondering whether one could generalize to other groups beyond GL2, what's done in his paper, at least epsilon of it. And so what's important with GL2 in the study of modular curves is the fact that there is a Jacobian where you can embed the curve. And that's why we leaped forward to threefolds and not like abelian surfaces, because these threefolds will be classified by a Shimura variety for U3. And that's these are Shimura varieties which have non-trivial Albanese. So yeah, if you're already wondering why we go to threefolds. So we'll fix L yeah, to be a prime number, and K will be a number field. And the question I'd like to talk about today is a generalization of a theorem of Manin, which appeared about the same time as Mazur's Eisenstein paper. So it's a pre-Faltings result. So it says that there exists a R which only depends on L and K, such that for any non-CM, that's important, non-CM elliptic curve, E over K, E bracket, so the L to the R torsion does not contain a K rational line. Or equivalently, the image of the mod L to the R Galois representation. So if you consider Gal K, which is the absolute Galois group of K bar over K, absolute Galois group of K. If you consider the action on so the L to the R torsion, yeah, this thing. So that thing is isomorphic to GL2 of Z over L to the RZ. So the image of this Galois representation is not contained in a proper Borel subgroup. And I just want to mention that the non-CM condition is optimal, because if you have a CM elliptic curve, once you have a field where it acquires, where the CM multiplication is defined, you will never be able to put the image into a Borel, okay? Because it will be a normalizer of a Cartan. So, yeah. Yeah, right. Okay. So, okay. So here is the generalization that we propose. Okay. So we take M to be imaginary quadratic field because K will be for open compact subgroups, I guess. So imaginary quadratic okay, so that's a technical but important assumption of odd fundamental discriminant minus D. So I recall that this in particular implies that D is 3 mod 4. In which our prime L is inert. So this is the interesting case from the point of view of Shimura varieties. Yeah, it's a more interesting case where it's a group which locally at L it's really a unitary group and not as opposed to GL3. Yeah, so this is the interesting case, and you fix S to be a finite set of places of K. So there is theorem A, which is the following, is that there exists R, which only depends on L, K, and S, such that for any non-CM abelian threefold A over K of Picard type, and Picard type means principal polarization and OM action. Okay, so there are variants where the action is by order, this or that, but I take the most common Picard modular surface, which corresponds to like principally polarized and action by the integer ring of M. So for all abelian threefolds of Picard type, okay, so theorem A, which we suppose this condition, which are semi-stable, outside S. A bracket L to the R does not contain a full K rational flag, or equivalently the Galois representation, so gal K acting on the automorphisms of O mod L to the R O, I guess that's O. Okay, no, maybe O is, okay, O is the completion, okay, I'll write it. So this is isomorphic to GU3 of Z L to the R. Z. The image of this is not contained in a Borel, is not contained in a proper Borel. In a Borel subgroup. And O is just OML. Recall that L is inert in M, so basically this is isomorphic to ZL square. Yeah, I'll avoid. Thanks. Yeah.
Precise what you mean by non-CM, because you said that you have OM action.
Right. The non-CM, like a non-CM abelian variety. So here, so this is one of the results, which is about full irreducibility. So it can have a CM factor that's okay. It can have like a elliptic curve tensor OM kind of things. It doesn't have to be. I only exclude like a CM abelian variety, like the worst possible case. Okay. Oh, this doesn't really have this. Let's see this. Okay. Okay. Gee, this is not ideal. Let me try the other one. Okay. Right. So there is no the semistability condition in Manin's theorem. I mean, conjecturally it shouldn't be there. So there is a theorem B without. So relaxing semistability. So requires to put gross level structure at D. So let me explain. So you need like a little bit of level structure. So for any V which divides P which divides D, so for any ramified prime, so P is basically V square. So if you consider, so the Gallo representation, so this is, let's say, like this is rho AL, and if you consider rho A P like bar, so on the P torsion, or rho A V maybe, I mean it doesn't matter. Yeah. Because P is a ramified prime for the unitary group, so the unitary group is with respect to M. You go to GO3 FP. Okay. So this is the automorphisms over FP of the V torsion. Okay. So then you can go, you can projectivize. You can go to PGO3 FP. And there is an exceptional isomorphism between PGO, which is the same as PSO, and PGL2. Okay, and once you're in PGL2, so that's canonical, all this. Once you're into P is odd prime here, okay, remember that I assume D to be odd, and this is one of the reasons. So once you're in PGL2, there is a unique index 2 distinguished subgroup, which is PSL2. So you can go to plus or minus 1 canonically again. And I denote this map epsilon AV. Or maybe let's keep P because it's more convenient. Yeah, go ahead.
What bar?
Bar means like mod V. Mod V. Just this is the action. Just this is the Gallo action on the V torsion. P is inert. So, sorry, P is ramified. So okay. And so here is theorem B, which basically, allows to remove this semistability. So there exists R this time, which only depends, like in Manin's theorem, on L and K, such that for all non-CM abelian threefold A over K of Picard type okay, such that if you consider epsilon AD, which is the product of those epsilon AP, so there is only one condition. It's not like one condition per P. It's just for this one. Such that this one is trivial. So that's a quadratic character, goes in plus or minus 1. So this is trivial. The same conclusion. So AL to the R does not contain a full K rational flag. Okay, so that's the main result, and I'll show in a second that actually theorem B implies theorem A. And so what I want to say is that I will move to a modular setting pretty soon, and I want to insist before going there, even that, so these results about non-existence of a rational line or rational flag, they're much more subtle than the results about non-existence of a rational point. So if you consider like Mazur's work, the results about x not n are much more subtle than x1 of n, and like those that have been generalized for general number fields are, for example, by Luc Merel, Kamieni, and others, are the one about x1 of n. So here you should think that we are working with a kind of a x naught of something. Yes?
I actually wanted to ask what you mean by these finite points do not contain a rational line. What is the meaning?
The image is not in a Borel. So, okay?
Borel would also be in an algebraic proof, right? I mean, or is it for this people?
No. We'll see in a second. It's a rank 1 group. There is a unique Borel up to, yeah, this will be another comment. Yeah, so if you think Galois-wise, just think the image is not reducible. Okay, not fully reducible. Okay, so let me explain how theorem B implies theorem A, and then we'll focus on the proof of theorem B. So, so we consider this epsilon AD, which goes from gal K into plus or minus 1, and actually it defines a well, a possibly quadratic extension. So that's inside plus or minus 1, and the condition would be that that's trivial. And so for all v, this time not dividing d, for, yeah, maybe I should call it w, just to, for any place not dividing the discriminant, the inertia here, okay, so we have, well, I'm assuming that A is as in theorem A, right? I'm trying to deduce theorem A from theorem B. And by this semi-stability condition, we know that for example, by Grothendieck's monodromy theorem, that this thing here, it's a pro-D group. And recall that D is odd. And so if you have a pro-D group inside plus or minus 1, this means that this image by epsilon AD is 1. And so this means that K prime is unramified outside outside the D, basically, and it's at most quadratic. It's a quadratic extension unramified outside a fixed set. So by Minkowski, all such K prime, because there is one K prime per A, all such K primes are inside a fixed number field K double prime. And then you just apply theorem B to, I guess, so R for the theorem A, if you want. It's enough to take the R from theorem B for L, K double prime, and D. Okay, so that's the proof of this corollary, yeah, which is kind of important because supposedly it's easier to check that something is semi-stable than to check this epsilon condition. Okay, so let's now move to the translation of this result into modular terms. So abelian threefolds of Picard type are, without surprise, classified by Picard modular surfaces. So so let's quickly recall what is Shimura surfaces of Picard type. So the reductive group, which I denote G tilde, is the unitary simulative group. So it's a GU M cube. Okay, just to be precise, doesn't matter for the talk today. Okay, so there is a unique, by the classification of reductive groups, there is a unique split U3 over Q. So it can be represented by this form or some other favorite form you have. So G tilde is the unique unitary group, quasi-split unitary groups in 3 variables. And you consider H tilde, which goes from the Deligne group into G tilde of R, which again, just for the sake of completeness, as giving the formula, but probably it's not important for, I mean, certainly not important for what I'm relating today. Z minus, okay. So this is a Shimura datum. And for any open compact subgroup, K tilde into J tilde of the finite adels. So we are over Q. Huh? So here the base field is Q, I is the adels of Q. So there are relative versions for CM extension of a totally real field, but for this talk we stay over Q. So for any such field, there is a quasi-projective surface whose complex points are given by the usual double adelic quotient. So H is the set of GR tilde conjugacy classes of H tilde, and more down to earth, H is a form is a complex is a ball in C2. So the locally symmetric space for a modular curve is the ball, the unit disk in C, and here the compact version is a ball in C2, or you can also realize it as some kind of a unbounded symmetric domain. Okay, so that's I'm just recalling the usual definition of a Shimura variety. Yeah, maybe. Yeah, okay. Depends. Okay, to put something at infinity as well, right? Okay, so so here is the thing. So
You put H, so you don't have to put H.
oh, okay. Sorry. Yeah, I wanted to do something different in my notes. Okay. Yeah. Thank you. Yeah. So so what I wanted to say is that this Gross's condition of like the image being inside like some kind of an index 2 group in GO3, this defines canonically an index 2 subgroup of the standard maximal open compact. So don't go below this, huh? Okay. Actually, yeah, it's very good to go on the other board because it was about Gross's condition. So this this condition of Gross, which I keep a little bit longer on the board, is that so this condition defines a index 2 subgroup, which I denote K double prime for some reason. Well, the reason is that K prime is for the other maximal compact usually. So this is the standard maximal compact, meaning the one that fixes a self-dual lattice with respect to the Hermitian pairing. And so here is our modular interpretation. So an abelian variety over K, as in theorem B. The second theorem, right? I didn't. Actually, yeah, in my notes, I don't know, I stated the first theorem B. So theorem B implies theorem A. Yeah, so as in theorem B, defines a point on Y, K tilde double prime. Okay, L to the R, I'll have to explain like what's this. K rational point on this, okay? Where K tilde double prime B L to the R means just matrices which mod L to the R fall into the Borel. These are like elements of K double prime tilde whose reduction of the L primary part, whose reduction mod L to the R belongs to B. I mean the okay, so there is a small exercise in this because well, we said that we don't want a K rational line, and there is a one Borel per line. So a priori, when you consider abelian variety such that the Galois representation has a stable flag, they go into some Borel. But by Iwasawa decomposition, all the Borels are integrally conjugated. So like for modular curves, each time you have like an elliptic curve with a stable line, it gives a point in the same x0 whatever. So this uses Iwasawa decomposition. Okay, so now, yeah, we can, if you want, forget the abelian variety business. So we just have a Picard modular surface, and we want to say something about the rational points. So the problem and also the exciting part of all this project is that there is no an equivalent of Falting's theorem. So you can prove like this Manning's theorem very easily using Falting's, because well, all you have to show is that your modular curve has genus at least 2, and then by Falting's you have only finitely many K rational points. And then I didn't mention this, but like both Manning's and our result are obvious for a single non-CM abelian variety. The whole difficulty is in making it uniform in the abelian variety. So, but unfortunately, so there is no general theorems about rational points on surfaces and even on modular surfaces. So for example, this is known to be of general type, so they're conjectures of Lang, but these are only conjectures. Okay, so right. So what is our aim? Okay, so the aim is to show that for R large enough, this Picard modular surface all to the R has well, either no or finitely many. Okay, let's say first finitely many non-CM K points. There's only okay, and so the key to this is the following proposition. Okay, so assume. Yeah, actually, I had to resume this from the beginning. So D is not D3 poses some trouble. So assume that D different from 3, and let H be the class number of M. So the proposition is that the irregularity of the minimal compactification of this, okay, I'll put gamma, so okay, gamma means I'm taking, okay, so let me explain this. So this is the irregularity. I recall the irregularity of a projective surface, so X projective, so this is projective algebraic surface, is the dimension of H1 XOX. Okay, so that's the irregularity. And so this is minimal compactification. So it just means that our quasi-projective surface, we add a bunch of cusps to do the Bailey-Borel-Satake compactification. Gamma, just replacing K by gamma, means that we have taken a connected component because we don't want to grow the genus of a curve for regularity by just making it disconnect. Okay? Okay, so this just means this is just a notation for K double bracket tilde B, our open compact subgroup, intersect G of Q. So this just means we have taken a connected component of our Picard modular surface, and we claim that the irregularity is at least 3. So this means in Albanese terms, this means that so the irregularity of a surface is the dimension of its Albanese. So this means that there exists a map from our surface into an abelian variety. So this is abelian variety of dimension Q, such that the image linearly generates the abelian variety. Okay. Oh, what the hell I'm saying? Yeah, such that image generates linearly. The same thing that a curve does to its Jacobian. So this is the reason we moved from elliptic curves directly to abelian threefolds, because the modular surfaces, like Hilbert modular surfaces, they all have trivial Albanese. The H1 of a Hilbert modular surface is always trivial. So you cannot have a non-zero map, non-constant map to an abelian variety. And yeah, I mean, much of arithmetic results on rational points relies on maps to abelian varieties in the current technology.
Y stands for this Y gamma B, or it's just a notation, or what is this I without anything?
I?
Y.
No, this is just, was defined just below, I guess. This is just the double adelic quotient, right? And then you take representatives and you write it as quotients of, so if you can, so the connected components of this Shimura, so the Shimura varieties are usually not connected, right? I mean, they are connected components. So the connected components of this are isomorphic to this Hermitian domain, quotient by arithmetic group, which I call this gamma. I just keep the notation. I keep the decoration. So there is an exercise here, which is not true for Hilbert modular surfaces again, is that all connected components, because it's an honest Shimura variety of PL type, they're isomorphic. So they have the same irregularity, etc. So this is not the case for GL2 of a quadratic imaginary, real quadratic field. In van der Geer's book, this is explained by genus theory. So there are different Hodge numbers, but that's not the case here. So you can just take the, any connected component is isomorphic to the connected component of 1.
I think this question was, what is the y without the subscript? What do you mean? Because you wrote y.
No, why is this?
Okay.
Yeah, I mean irregularity. Yeah, okay. Okay, so once we have this map to an abelian variety, let me see how the theorem can be deduced from such a proposition. And if I have time, but I doubt it, I can say a few words about the proof of. So this proposition basically is a theorem of existence of modular forms of low level, if you think about it. So right, I mean, so this would say like that the genus of a modular curve is at least something. So you have to create morally like Picard modular forms of level just L to the 4 or lower. Okay. So there is a corollary of proposition, which, well, it can be called itself a theorem, but it's really a consequence of this proposition. So this is due to Ulmo-Yafaev and a previous paper of ours. So if you have a surface such that the irregularity, the fact that the irregularity is at least 3 is enough, implies that the Bombieri-Lang conjecture holds for y. What this means? This means that for each k, I mean k was fixed, a number field, there exists z, a curve in y, such that there exists only finitely many k rational points in y outside z. Yeah, maybe I should have said here what we have shown is that y is of general type, and the Bombieri-Lang conjecture holds for, which says that if you have a surface of general type, then there is a curve such that there are only finitely many k rational points outside this exceptional divisor. So you cannot exclude, for example, the Picard modular surfaces. If you consider the so-called toroidal compactification, you are adding elliptic curves at infinity. So you cannot exclude the possibility of some exceptional divisors where you have infinitely many rational points. But once you exclude such a exceptional curve, there are only finitely many points. And right. And so let me then state a lemma and explain how we deduce the theorem from this corollary. So the lemma it's a very down-to-earth lemma, but it's extremely useful. So the lemma is very simple: is that this gamma double prime. So gamma double prime just means you consider just k tilde double prime intersect g of q. So you don't put this condition at L, just this index 2 subgroup of the, so this is just the index 2, so this is index 2 subgroup of the Picard modular group, which is SU3OM. So this is the classical Picard modular group, okay? So you have an index 2 subgroup, okay? And the lemma is that this gamma tilde does not contain complex reflections. So what is a complex reflection? So gamma, so this is maybe the occasion to point out that my subgroups, they have torsion, okay? It's like gamma 0 of n over the modular curve. So I have torsion. So I'm not in a neat or anything case. Okay, we're in a very low level. There is torsion, but we don't want to have a very specific kind of torsion, which fixes a curve. So we allow only torsion which has isolated singularities. So the fixed element, if you have a torsion element, either it fixes an isolated point, that's okay, or it fixes basically a hyperbolic curve, right? And that, because of this is index 2 gross condition, miraculously doesn't happen, and this is really crucial. So the proof of this is just one line, is that so otherwise, so if you have such a complex reflection gamma, otherwise gamma mod p is well, the joint of 1 minus 1. So this is seen as an element in PGL2 FP, which I explained is isomorphic to PSO 3 FP by the joint representation. I mean, this is in PGL2 and the joint is in PSO. But what's happening is that the product for P divides D, oh, I know I shouldn't write here. Okay, I'll do this for last time. This product is minus 1 over D, and this is minus 1. And that's a contradiction because we assume that we are not in the subgroup. The determinant cannot be minus 1. Okay, so there is no complex reflections. So let's explain how this allows us to so how the irregularity allows us to finish the proof. So okay, okay, remember, like we have our Picard modular surface y, and so far, so by the proposition, we know that the rational points lie on a bunch of curves. So this is like Z. It's like a bunch of curves, and they're like a finite number of points outside. And what we want to show is that there are only finitely many k rational points on such a Z, right? I mean, and then, okay, the final step will be to take a R for each one of them. So, okay, so proof of theorem. Oops, let's stay with the black. So proof of theorem. Okay, so take C a geometrically connected in Z. So in this exceptional divisor, let's take a curve C. So if C has genus at least 2, then there are only finitely many k rational points on it. But we don't know that. It can very well be a genus 0 or 1 curve. So without, so here is where the lemma is really crucial, is that because the singularities of my Picard modular surface are isolated, okay, so the lemma implies that the Picard modular surface Y has isolated singularities. So this implies that C, if you remove a bunch of points of C, so these isolated singularities, so this implies that there exists U in C open, which is endowed with an abelian family. So that's the key. Like there is no, you see, we are in a very low level. It's like the J line or something. There is no universal abelian family over the whole thing. There is just such a thing over an open. But the open here means you exclude some curves. So if you want to say something about the rational points of these curves, you better have some abelian family over these, okay? This is really crucial. Like, so the lemma implies that there exists U endowed with an abelian family. I mean, abelian family means like a family of abelian threefolds of Picard type A over C. Okay, so that's really important. And then, okay, I'll be short here. So once you have a curve with an abelian family,
Over U or C?
sorry, over U, yeah, over U. I'm sorry. Over U, thank you. Once you have an abelian family, you can invoke results of Kadore and Tamagawa, among others, and say something. So what they have shown is that, well, okay, so Kaduge and Tamagawa have shown that for every number field K, and for every K rational point, well, they have shown that there exists some universal R1, like some integer, such that for each K rational point, so this R1 just depends on the curve U, I guess. Okay, I should maybe move to U. But I can put back C because, yeah, okay. U and the number field K. So there is a R1 such that for any K rational point, okay, so the index, I'll define these things, is uniformly bounded. So what is this? So this is, so gamma C, so basically is the Mumford-Tate group of the family. Okay, so this is like the Mumford-Tate group of yeah, okay, of the family A U, and this is the Mumford-Tate group of just the abelian variety of AX, which is the fiber. Yeah. So they've shown that the index of the integral Mumford-Tate group is uniformly bounded in this family. And then, okay, by general considerations, this Mumford-Tate group, I mean, it's not abelian. It's not CM because you cannot put CM abelian varieties in a family. I mean, they are isolated points in the moduli space. So the Lie, by general consideration, the Lie of gamma U tensor QL. So that's a Lie algebra in U3. It contains SU2. SU2 QL. So that's just obvious. And because it contains this, gamma U, oh yeah, I hate changing words so often. I'll try to squeeze it here because otherwise you'll have to look at too many places. So this implies that gamma U contains the exponential of SU2. SU2 is SL2, I mean, L to the R0 ZL, right? I mean, if a Lie group, I mean, just by the classification of, these are Lie groups of small dimension. And because this index is bounded, so that's an exercise, if you have a Lie group which contains SL2, if you want, of 2 L to some power ZL, finite index subgroup, this means that there exists some R1 such that gamma X contains the same thing with R1 here. Exponent of SU2 L to the R1. And basically this means that it's not contained in a Borel mod modulo this, right? If you have a copy of, this means that modulo L to the R1, if it contains a copy of SL2, the Lie group, it will not be contained in a Borel. Okay, it's not contained in a Borel, and that's basically the uniformity result. Yeah. So okay, maybe okay. There is one last step. So there is one last step, which is I already mentioned it orally, but let's write a line. How you treat the finitely many remaining cases. So far, what we have shown so far. So far, using this previous result on Bombieri-Lang plus Kadureta-Magawa. So far, we have shown that. So far, outside a finite set of points in Y, and when I say a finite set, we have thrown out. Remember all the isolated singularities, and then for each curve we have thrown out. Here also we have thrown out a finite set of points. Yeah, okay. So this U is probably shrinked. I mean, U is open in our curve. So outside a finite set of points, we have uniform R, uniform boundedness, and so for each of the remaining points, finitely many points, well, either it's a CM point and we don't do anything. So either it is a CM point, and it's not that we don't want, but we cannot do anything because it will, once we over a number field where the representation is totally reducible, it will always be in a Borel modulo, even without going modulo power of L. Or it's not, or if it is not CM, then by the Mumford-Tate conjecture, which is known for U3, we know that the Lie algebra of the image will contain an SL2. Therefore, this can be detected at some level by the Mumford-Tate conjecture. Lie of this gamma x will contain a copy of SU2, some L Rx ZL, and then you take R KL in the theorem to be just the sup or the max of all these Rx's and this R the R before, like did I give it a name? R1. Yeah. So this was the idea of the proof: is go from so basically the three steps were: first show that the k-rational points are not Zariski dense, and amazingly that's the most difficult part, where it's used that you have an Albanese. Once they're not Zariski dense, they are on a bunch of curves, and for each curve apply Kadoreta-Magawa, and this was like something we overlooked first, because to apply Kadoreta-Magawa, you don't need just to have a modular curve, you need a abelian family on it, and it was important to ensure this by ruling out the complex reflections, over which there is no abelian family at all. And the last point is just to invoke Mumford-Tate conjecture and treat one by one the remaining non-CM points. Okay. I don't know. Probably I'll leave some time for questions because it's not really time to start the automorphic thing. Thank you. Yeah.
Are there any more questions?
Yeah.
Do you know anything about the rank of the Albanese one?
Yeah. The rank, you mean the irregularity?
No,
Oh, oh, the model. Yeah. So the Albanese in this case is completely determined by CM factors. So these are actually although the Picard model surfaces are much more complicated than modular curves, their Albanese are much simpler than the Jacobian. So basically, the factors of the Albanese are whatever corresponds to CM forms in the Jacobian of a modular curve. So as much as you know for CM forms over Q, you know here. But maybe let me check more carefully that I'm not over. No, there is. So this was, okay, because I motivated all this work, it was the way it historically started, like understand Mazur-Eisenstein ideal. So our first approach was to find rank 0 quotients, and you can find them, but in some cases, depends on what's D mod 16. So eventually, if you want to show an equivalent of Mazur's result of non-existence of rational points outside the infinity divisors, you will have to do something like this, find a rank 0 quotient. Yeah, absolutely. Yeah. But luckily here we don't have to, yeah. Oh, yeah. Yeah, I mean, you have to construct Picard modular forms and at a very low level, so this cannot be just some abstract result. And so part of the answer is what I just said to Jan. I mean, is that Hecke theoretically, Picard modular forms contributing to the H1 are just built of CM forms. So you have to, basically they're parameterized by Hecke characters of M. So you need the Hecke characters of load conductor because the conductor will correspond eventually to the level. So so here we use again like Gross's work on canonical characters. So for half of the discriminants, you just take Gross's canonical character. So Gross, right? I mean, what's called canonical character is a Hecke character of conductor basically square root of D. This always exists. Unfortunately, for half of discriminants, it has the rho and epsilon number because there is some condition of Rogawski. You have always this canonical character, but it goes to U3 if and only if, like for half of discriminants, if D is 3 mod 8. And when D is 7 mod 8, we need some tricks. And again, it's very explicit. So yeah, one of the pleasant things in this project is that, which I completely kind of hid here, maybe bad choice, for students, like you can really construct these Picard modular forms super explicitly. Like you can play with magma, find a CM form, or directly find a CM character, and compute with it, yeah. Thank you. It's small, right? I'm saying there's no like junk primes. Okay, so Mazur is better, of course. He does like x1 of n for n prime. No, small means that I didn't throw in all kind of auxiliary primes. There's like, it's ramified. It's like, okay, the easiest modular forms. So this we should think of it as weight 2 modular forms because they contribute to the H1, right? I mean, this H1 XOX, this is isomorphic to Hodge decomposition, right? So these are vector valued modular forms, as we saw a little bit yesterday, but they're the most simple. So these are sections of the cotangent bundle of a surface, okay? And so for example, for weight 2 forms, the easiest thing will be to have like prime conductor, right? There's no weight 2 forms of level 1. And here, okay, so actually, yeah, you're right. So what's happening is that, okay, I have L to the 4. but this is because I need the regularity to be 3. I'm already constructing a form okay, it was y for me, in y0l. I mean, I'm all L square actually, okay. So okay, in half of the cases, okay, let me put it this way. If D is congruent to 3 mod 8, then if you consider Gross's canonical character, you have basically a level 1 form. So it's let level 1 is in this index 2 subgroup, okay? So this was, okay. But when D is 7 mod 8, the regularity is 0. So if D is 7 mod 8, what's happening is that this doesn't have irregularity. The one just with L fails as well. Have to go to L square. The reason I put L4 is that you go to bigger dimension by old forms. So this is like the trick everybody uses, right? If you want to grow the genus, you just put all forms. It's much more difficult to find other new forms. The easy way is to put all forms. So that's the reason. But yeah, so okay, L4 can, yeah. Let's say L is in the problem. So I mean, and our result is about L to the R. So 4 is not a problem. What was really important to avoid is to have a result like you can say something on the L torsion if there is P torsion, right? I mean, this kind of statements, which is, right? Okay.
If there are no further questions, then this next one again. Where did the dinner sheet get to? That's it. Vanished off the. Yeah. Been eaten by somebody. Okay, we'll resume at 5 past. Well, there's coffee and posters upstairs now. We'll resume at 5 past 11.
Yeah, thank you. You sure it's recorded? Because it didn't make any unpleasant sounds.
What kind of unpleasant sounds should when I use your shirt here. It's gonna go in a pocket controller.
Inside.
Yeah, whatever.
All right, okay.
As long as everybody.
Thank you. So yeah, welcome back. We'll have posters throughout the week, so there'll be more chance to see all of them. Our second speaker for the morning is Dino Lorenzini from the University of Georgia, and he's going to tell us about tools and exceptional units.
Well, thank you very much. Thank you to the organizers, in particular to Daniel, for giving me the opportunity to speak here today. So let me just, since what I'm going to talk about is a bit not in the mainstream of this conference, I decided to keep the details at a low level. I also added some review for the graduate students, because I see that there are a lot of graduate students in the audience. And don't hesitate to actually ask questions. So most of what I'm going to tell you is about elliptic curves over number field. Everything that all the questions that I ask can be asked for a billion varieties over number field. but I don't know how to answer them. So at the end, so what I'm going to tell you is explained by the concepts of exceptional units and the Lenstra constant. I'll be reviewing that. And at the end of the talk, if I have time, I'll tell you what I know about the billion varieties over Q. All right. So curves and fields. So just to set up some notations, K will be a field, number field, or Q. L over K will be a finite field extension of degree D in this talk. And then we'll have a curve, X over K, genus G. And X of L will denote the set of L rational points. So if you are not familiar with schemes and you don't think of X over K as a scheme, it's perfectly okay in this talk to think about a plane curve defined by a homogeneous polynomial of degree capital D. And X of L is this set of points, right? I'm trying to get my hand to go straight. And in this case, the genus of this plane curve is bounded by d minus 1 times d minus 2 over 2, and equality if the curve is smooth. Right, and the definition that I'm making here, that I'm recalling also, a new point of X over L, that's an element in X of L that is not in any kind of subset or defined over subfields of L, right? And if you think of, in terms of schemes, looking for new points is the same as looking for close points on your curve with residue field exactly L, or isomorphic to L, right? And not a smaller residue field. All right, so elliptic curves, it's perfectly good to think about them as Weierstrass equations in this talk. They are curves of genus 1 with a choice of a point. When you put it in Weierstrass equation, the point is the point at infinity, although need not be, but it makes a better theory to take that point. The key fact is that E of K, the set of K rational points, can be endowed with a structure of an abelian group. P0 is the neutral element. And the Maudelvey theorem is that it's a finitely generated abelian group, so you can rewrite it as T, which is the torsion subgroup, a finite abelian group, times Z to the R, and this R is called the algebraic rank of E of K. All right, so that's, again, just review. If I'm going too fast, just make it known. It's dangerous to have a talk on slides and kind of run through the slides, so I appreciate like, slow down. All right, the basic question, all right? So the basic question in my talk is you give yourself a curve x naught over k of a certain genus, you give yourself an extension L naught over k of a certain degree, and you want to determine whether x naught of L naught contains a new point, right? So it's a point that does not exist over a smaller extension. Now everybody knows that this problem is too hard, right? So let me suggest two variants that might be more accessible. So in the first variant, you only fix the curve. So I fix the curve of genus G, and then I only fix the degree of the number field, D, and I ask, is there a point of degree D on that curve? Right? Supposed to be easier than the previous problem. You give yourself the flexibility to actually not set the field. And the other version is you fix the number field. You fix a number field of degree D, and then you fix a genus, and you ask, is there a curve of genus G that has a new point over that given field L0? Right? So two distinct problems, but equally as hard as I'll try to convince you. Now, in the first problem, once you've determined that there is one point of degree D, you might ask, am I in a situation with a D and the curve where I have infinitely many points of degree D? Right? And similarly, in the second problem, once you've determined that you have a field and you found a curve that has a new point over that field, can you find infinitely many curves that have a new point over that field? If the field is fixed, we'll let the curves vary. All right. So everything that I'm going to, the most of this talk will be on part A. Right? I'm going to actually look for special points that I will define on modular curves x1 of n when n is going to vary. But I couldn't resist telling you something about part 2. Right? So let me make a little detour on the question B. So again, the question is, you fix a number field, your favorite number field, and you ask, can I find a curve that has a new point over that field? Right? So when you start thinking about it, everybody will come up with this, right? Your field L contains an element that generates it. We're over a number field, so we have a separable element. And then you take the minimal polynomial of that element. That's f of x in my notation there. And then you look at the hyperelliptic curve, y squared equals f of x. And that has the new point, alpha 0, right? And what about the genus? So, the polynomial is separable. So this curve has genus d minus 1 over 2, or d over 2 minus 1. So roughly d over 2, right? And it's only going to go down to genus 1 if you're in degree d equals 3 or 4. Right? So the difficult part of this problem is to find a curve of low genus that has the point that you want. Right? And just to entice some people to actually, my set of tools may be different from a lot of people in this audience. So here's a problem that I don't know, but maybe with a different set of tools, one might do something. So just to set notation, zeta p will be, as usual, a primitive pth root of unity. And q zeta p is the cyclotomic field of degree p minus 1. And the question is, can you find an elliptic curve that has a new point over that field? I don't know how to do it in general. And it doesn't make it any easier to look at the totally real number subfield, right? But somehow these are special fields, so maybe special techniques. People could actually say, oh no, something actually forces me to have infinitely many curves of genus 1 that contain a new point over that field. So I'm leaving that as an open question. Let me tell you some positive results on that question. Okay. So I'm going to state everything for fields of characteristic 0. It gets a little more difficult if you do small characteristics. All right, so the first theorem that I know, which is with Qing Liu in Bordeaux, you fix a finite extension of degree at most 10. Then you can prove that there are infinitely many elliptic curves over that field, such that contains a new point over that field of degree at most 10. Right? So this is the best we can do in complete generality. And after we did that, we realized that Rohrlich had already done that up to degree 9 in 1997. We proposed a different proof of getting there, but we don't do much better. Right? So here, K is any field of characteristic 0. Putting number field does not make it any easier. I don't know how to do better by putting more conditions on the field. But you can do some extra degrees, right? 12, 14, 15, 20, 21, 30, if you ask for the field to be an abelian extension of a number field, right? So again, now you start looking in more details of what's going on, but you still cannot go to large degrees. And Arvind Suresh has the extra 16 where he can say something, right? So, and his condition is simply that LOK has to be Galois of degree 12, 14, and 16, then infinitely many elliptic curves have a new point over that degree of that field. Yes?
Sorry, in these theorems, they actually are able to construct elliptic curve such that contains a new point explicitly, or just
Yes.
proves that it exists in point?
No, for all these results, as soon as you get infinitely many, it's a construction. And you have a family, you have enough in the construction to say there are infinitely many. Yes?
In these results, when you get a new point, is it you get a jump in the rank, or it could be a torsion point?
It could be a torsion point, but most probably not. But you don't see, the proof does not allow you to make that difference. Right. Okay. And so just in general, the techniques of I've stated something as down to earth as possible to make it an approachable question. But in general, all these people do is, you know, if you have degree d, then you're going to find a hyperelliptic curve of what's genus d over 4. And in the last case, Arvind, putting a condition that there is a quadratic subfield in the field, he's able to go to d over 8. The genus is d over 8. But can't go, or none of these techniques produces small genus all the time, right? You kind of, there is some kind of bar that we can't cross.
So why you care about new points as opposed to just points? Like we only want to distinguish the ones that are not in a smaller subfield.
I just don't want, I mean, it's easy to cook up something that has a small genus as a rational point, and then that rational point would count, right? If that would be an example with a point over degree 17. I want to avoid something that comes from smaller subfield, just to make. All right. All right. What's next? All right. Okay. So we can't do number 7, degree 17 in my list, right? So can we do a field of degree 17? How would we do it? So I took one. You take the cyclotomic field of 103rd root of unity. 102 is 17 times 6. So there is a cyclic subfield in there that is Galois, beautiful field. Can you find an elliptic curve that has a new point over that field? All right. So the answer that I'm going to go through is yes, but you have to assume the Birch-Swinnerton-Dyer conjecture. So let me review what I need in this talk for the Birch-Swinnerton-Dyer conjecture. And for ease of exposition, I'm going to just keep k being q, and my elliptic curve will be y squared equals x cubed plus ax plus b, right? And the main idea in modern arithmetic geometry is that if you have an object over q, you should look at it mod p, understand all the mod p reductions, and then try to kind of package them together to recover some information about q, right? So the understanding of elliptic curve modulo p is Hass's theorem. The size of the number of points modulo p is bounded by p plus 1 minus 2 square root of p, and p plus 1 plus 2 square root of p. And then it turns out that this is the only number that you need to package because the elliptic curve has genus 1. And you create a function out of them. Let me just go through unmotivated definition of the L function. So AP is going to be p plus 1 minus the size of the number of points mod p. And you define a product for all primes of a quantity here that comes from the characteristic polynomial of Frobenius, but you can just write it like this, right? If I'm thinking of people who have never seen it, that can take that as a definition. And you do that for every places p, or every prime p that does not divide delta. When p does not divide delta, then the elliptic curve in reduction is again an elliptic curve, and you have this AP at your disposal. And then to get the L function of an elliptic curve, you multiply by some extra terms for each p that divides the discriminant. And in general, these terms are there to make it a better behaved functional equations, right? But the meat is really in this expression here. All right, and then the first part of the Birch-Swinnerton-Dyer conjecture says the following. So here k is any number field, E over k is an elliptic curve, it has an L function, and the rank, algebraic rank R, that means the rank of the Mordell group over k, right? And so the conjecture said that this L function is actually a holomorphic function around s equals 1, and we can consider its order vanishing that I'm calling R analytic. So written in simplest term, it says that you can actually develop your function along at s minus 1, and you start with a constant L0 times s minus 1 to this analytic rank. And the miracle is, the conjecture is that this analytic rank should be the same as the algebraic rank, all right? And in my next slide, I'm going to kind of give you an example why this is really powerful. But in words, the analytic rank, we have a chance of computing it directly. This is the hope. But the second part, the algebraic rank, so far we have no chance of actually saying much, right? In general. Okay, so back to my example of degree 17 field, right? So I want an elliptic curve with a new point over that degree 17 field. I'm going to run through Cremona's table, and it is kind of called the L function in modular form database, right? As we were told by Gonzalo yesterday, but in my mind, I'm old, this is Cremona's table. and we compute. And the miracle is that you can compute this analytic rank, at least up to, when the rank is supposed to be 0 at bigger than 3, it's probably correct. But nevertheless, you can actually run through 2 computations, right? And I'm really thankful for off-the-shelf tools to do things like this. It's crazy. I mean, this is a degree 17 field, and I need to go through all Cremona's table. Because what am I looking for? I'm looking for a difference, right? I want the rank over Q to be less strictly than the rank over L, and that would mean a new point, and in fact, a new point of infinite order in my elliptic curve, right? So now it's just a matter of can you do the computations or not, right? And there is one, right? So this is, I'm going to use this. So this is in the middle of Cremona's tables. You have to go already quite far, right, to find one. I thank Bill Lambert in Bordeaux and G.P. Parry who found it for me. And explicitly, it's given by this equation, right? So it's rank 2, it has only 3 primes of bad reduction, and supposedly it has analytic rank that jumps. So the question is, now that you know the equation, can you actually find a point, right? I tried to run the same examples with primes of degree 19 and more, and I did not find one in Cremona's table. It just means that they are too short. Even though you have gazillions of curves already, the conductors are not that big, and to find one with that kind of degree 17 points, you need a large conductor, it seems. Right? I don't know if it's true, but it didn't find it. All right. So yes, so we can compute this kind of things. You have to be careful when you use tables or magma. Sometimes you find mistakes, right? You have to send back your. So here, for instance, we found things where the rank was the computer decided that something was 0. But it was not 0. It was 0 a very long time, right? So once you notice something, you send it back to Magma, and somebody nice on the other side tries to fix, right? To how changes the parameters so that you actually compute far enough to discover that the thing is not 0. So computations are great, but you want to still know what you're doing when you compute. All right. So now I'm going to switch to the part of the Birch-Swinnertmeyer that I want to use in the rest of the talk. So that's the second part. So the second part says...
in the previous example, you find a new point on the curve?
No, I don't know.
So are you making a point that because of Galois conjugates, like this Rn of L is like 16 or something?
Right, so this is going to jump a lot when it jumps because of the Galois action.
So like you have to be careful numerically, that's what you're saying, because it vanishes to a very high order.
Right, but I'm saying if this computation is about finding something that vanishes and then does not vanish, but vanishing is a hard thing to actually certify numerically, right? So or not vanishing.
You don't compute the analytic rank. You just need to compute the second derivative and show that it's 0 or something.
No, but it's the 16 derivative. So how do you know that the 14 derivative is actually 0? Oh, because of the Galois conjugates.
No, but you don't need to go that far. You just need a strict inequality. So as long as you go beyond 2, that's enough.
But you cannot show it numerically as 0.
If you're assuming BSD, yes, because you have a lower bound for the special value.
Just need to compute the function of regular form twisted by a character.
Good? All right. Okay, so I'm moving on to a new topic. So that was my tangent on my problem B. I'm going to talk about things that pertain to this question A. All right, so the second part of the Birth and Sweeten-Dyer conjecture states that the leading coefficient there is given by an explicit formula. All right. Now, for this talk, the only part of the explicit formula is what I have here in the red. All right, I'm not going to go into all the terms and review everything, but the leading part here is a product of CMs. It's called the product of the local time eigennumbers. And then the denominator, I have the size of the torsion squared. All right? And what I would like to talk for the rest of the talk is, suppose that you have a torsion point on your elliptic curve. So you have a denominator on that formula. Can you cancel? Now, do you expect to actually have a cancellation that this prime that appears on the denominator also appears in one of the time eigen-number? Right? So that's my.
M stands for subfields of L.
I'll define this in a second. M stands for all places of K.
All right.
Let me define it. It's right here. So, right. So I'm going to define this number CMs that appear on the top. So in the simplest possible way, for each maximal ideal of OK, I have its residue field. And I take an elliptic curve defined over K. And the theory tells us that there exists a finite abelian group called phi EM of Km. And most importantly, a group homomorphism from EK into that finite abelian group. Right? So the words that I should be using here is that the elliptic curve has a Néron model. The Néron model at M is not connected. I have a connected component and the group of components. So phi EM is the group of component of the Néron model. I plug in Km and I get a finite abelian group. But the thing to remember is that you have a nice map, right? A group homomorphism. So the time eigen-number is the size of that group. We forget about the group structure, we just keep the size. And again, the thing to remember is that if you have good reduction, then it's 1, right? The Néron model is connected. I have an empty curve in reduction, so there is no time eigen-number that is of interest. So these little guys appear only at the places of non-good reduction. So here's an easily explained cancellation, right? If you had a torsion point in E of K of order n, you push it into one of these groups. If it survives, that means that n has to divide the time eigen-number and you cancel, right? So I just want to point out that the quotient of the product of all the time eigen-numbers by the image of the elliptic curve is studied in Chile by Christian Gonzalez Aviles. So if you have questions about this, here's the reference. All right. Okay, so let's start with that question of, do we have cancellation or do we expect cancellation with elliptic curves over Q? So my initial motivation is that I heard from Amor Dagache that he had used Cremona stable and he had checked for Cremona stables, if you had an elliptic curve with a torsion point of order 5 or 7, then 5 or 7 had to divide the product of the time eigen-number, which is called the global time eigen-number, right? And he conjectured that that should always happen. Once you make enough computations, you believe some statements, right? That's the power of what we have now about being able to make computation that we didn't have 40 years ago. You can make a conjecture here and pretty sure that is correct. Right, so the conjecture is indeed true in full generality. So what I can prove for elliptic curves over Q is even slightly better. If you take an elliptic curve over Q with a Q rational points of order n, which is 7, 8, 9, 10, or 12, so the largest by Mazur's theorem that the torsion can be, then n has to divide the product of the Tamara numbers. All right, and then for 5, because this also takes 5, then there's a little twist in 5. 5 is that n divides the Tamara number except when the elliptic curve is x1 of 11. All right, so we go back here and we see that I put the word optimal. And optimal means for an elliptic curve that you are x0 of 11. So x0 of 11 is the optimal one. x1 is in the isogeny class, but is not optimal. And here we don't divide. All right? So there's no contradiction between what Ahmad was saying and that theorem. All right, so what I want to do for the rest of the talk is discuss how does this, is there a generalization of this to number fields? Right? Are there elliptic curves where you can cancel or not cancel? Right? So as you're going to see, the general trend is that you can always cancel, except a few cases. All right, but before I go into number fields, let me tell you a little bit more about Q. What about if you had small torsion, right? So maybe if you had a torsion point of order 2, 3, 4, or 6, could you still find the divisibility? And the answer is yes, there are some conjectures of Agassi and Stein, but you need to consider the full leading term in the Birch and Swinner-Dyer conjecture. So let me give you one example, due to Mencelos Melistas. If you take a semi-stable optimal elliptic curve over Q of rank 0, right, then the torsion part divides, okay, the usual thing, the product of the Tamara numbers, but then you have to put some other terms, so the Shah and the number of components of E of R, right? And this becomes completely different to prove because you have to show, that Shah is not trivial. So I'm going to keep it to easy things. This is much harder, right?
So the sentence before the conjecture, the statement of the conjecture, or is it consequence of the conjecture?
So the conjecture is more general than this. This is just inspired by this, what he could prove.
Oh, but I actually mean the sentence before that. Like the yes, but one needs to consider the full leading term.
Right, so this conjecture here says that under certain condition, the torsion part in the elliptic curve divides something that looks like this here, which what I'm using, and then some other stuff.
Relating to the previous slide, one expects that the square of the torsion divides like the CM over the square of the torsion is an integer or no?
Say it again. You expect?
One expects that this torsion divide, like the square of the torsion divide the Tamara number or no?
So that's not always true. I mean, when n is large, yes, this 12 square divides, and I'm pretty sure here they all divide. But for 5, 5 squared, well, already 5 does not divide, but even 5 squared, I'm not sure if I can say it's only finitely many. Yeah, so that's a good question. I don't know the exact details there. Somebody needs to do it. Good? All right. So where am I? Right. So this is only what I'm going to say for small torsion. Right. Small torsion creates problems, and we all know. So things are harder. All right. So elliptic curves over number fields. So the notation is K over Q is going to be of degree D. I'm taking an elliptic curve with a K rational point of prime order n. So from now on, n is prime. Right? And I'm going to give you some theorems, but at first I try to set up the general framework that I think might be correct. All right, so I'm going to call that hoped for theorem. It's not a theorem, and it's not even a conjecture, okay? Don't cite this. But I think it gives the framework that I'm thinking that I'm working with to try to push. So, so this is saying that you should expect the divisibility. You should expect the cancellation in the ratio product of the Tamaga number divided by torsion, except for finitely many exceptions, if n and d are in a certain range. All right. So I'm saying so. So let's see why there is something to be said, right? But an elliptic curve with a point of prime over the n over k, that's a point on x1 of n. A k point of x1 of n. x1 of n, the modular curve that classifies pairs, elliptic curve, and point of order n. Right? So if n is too big, rather if d is very small, you don't expect any point over k. Right? And x1 of n, it's usually a hard theorem, but if d is small, you don't have points. If n is large, d is small, there are no points. So my theorem is useless. There are finitely many expressions. There are no elliptic curve at all, right? With cancellation or without cancellation. And then if you put d too large, then you start to have infinitely many exceptions. Right? So there's a range where I hope there is a theorem of finitely many expressions. All right? So let me give you the first 3 examples where somehow I can prove this. So this is what I already told you, right? Put in that context. D equals 1, so it gives me only one field. N is greater or equal to 5, so I'm avoiding small n's. And then n divides the product of the Tamaga numbers, except in one case, x1 of 11, and when n is 5. Right? No exceptions for 7. All right. So the next theorem now is for quadratic field. So here I have to move up. I have to take, it's a theorem about n at least 7. But again, I'm able to show finiteness. So what does it mean? It means that I have a cancellation in my ratio, except over 2 fields. And for each of these fields, there are 2 elliptic curves that don't produce a cancellation. All right? Again, the new part here is that this is a theorem for all quadratic fields, not just for Q, right? So this is excluding infinitely many, I have to deal with infinitely many quadratic fields and get a finiteness out of that. And then for d equals 3, again, I have to go to n equals greater or equal to 11. And again, only one exception. And for 1 prime, 13 over one specific field, Q zeta 7 plus. Right? Otherwise, there is a cancellation in this leading term of the Burchard-Swindler-Dyer conjecture.
But n equals 4 for Q, you say it's not true.
So n equals 4, I did not, oops, I want to go back there. N equals 4, you're saying here? Right, so here I'm just saying n has to be bigger than, did I mess it up? N is prime. Yeah, no, you're right. yes, there should be a general theorem, but it's going to be more complicated if you allow n to be not prime. Absolutely. Yes, so from now on, n is prime. All right, so just to be clear, I can find the elliptic curve, right? This theorem says there are exceptions, but we find them. Here I'm just going to give you the J invariant, or the elliptic curve actually can be defined over Q. Every time you find an exception, namely where you don't have a cancellation, the elliptic curve is extremely simple, very, very low conductor. In general, the product of the Tamaga number is 1. So this one has 1 prime of bad reduction at 3, and the reduction is I1, so trivial Tamaga number. Okay. So while I have this, you might think that this problem has to do with cyclotomic fields, but then you go to d equals 4 and you realize that the exceptions are not anymore cyclotomic, right? So it's just the first 3, you get cyclotomic field. All right, so here's the the last case where I can actually prove something without conjecturing anything. So d equals 4. At this point, I'm for n prime bigger or equal to 11. And the theorem is that if OK has rank 1 or 2, right, then we have a divisibility except in 3 fields. Right? So let me explain this, this table here. I'm giving you here the polynomial of the field. That's the rank of OK star, and that's the discriminant. Right? And then here I'm giving you the exception. So n is going to be what I said. So this table says, let's look at this 11, 2. This says that over that field here, there are 2 elliptic curves with a point of order n and no divisibility. Right? And there is also over the same field an elliptic curve of with a point of order degree 13 with no divisibility. And since the J invariant is easy, I wrote it down. Right? In general, it's a complicated equation. You see nothing out of the equation. Let's put it like this. Right? And then over that field, I'm claiming here that there are 4 elliptic curves with a point of order n and no divisibility. And on this one, there are 2 only. All right? And for those of you who wonder whether with 11 you always get something even, yes. If the field does not contain q zeta 11, you can prove that you find 2 exceptions when you find 1. Okay, so the next statement, right, one has to do all ranks, and you can still have something that is totally real in quartic fields. I cannot prove it, but I can make a conjecture. So here, when the rank is 3, right, I'm claiming that there are only finitely many exceptions to the divisibility. Everybody has a cancellation in their ratio except for that over that field.
Those theorems, how do you, in simple words, compute explicitly the exceptions?
I'm going to tell you.
Right.
Yeah. So everything I can compute it, and that's the rest of the talk. Right? How do you prove a theorem like this? So here, 3 primes appear. So 2 elliptic curves with a point of order 11, 1 elliptic curve with 13, 1, 17. Yes?
Which is the rough date by the condition the rank 1 or 2 in the proof in order to understand that you cannot use the same proof for rank 3?
Say it again. So I have a proof for the first 2, and for the third one,
Yeah.
I need something about the Letzra constant that I cannot prove. So I'll get to that. So I'll explain why this is proved and that is not proved. Right? All right. Okay. This curve here with the 17 was found around 2013 by David Crum. He had an algorithm to list points of low heights, and he succeeded to search and find one. I must say that the fact that he found that kind of convinced me that it was time for me to actually make computations, that it was useful, that we were ready. We could work in number fields of high degree. Right? 4 is not that high, but you can try higher. Right? Now, these fields, I'm going to lead you in somewhere that is better than the previous slides had fields that were all cyclotonic. Now, what is special about these fields?
The question is it a coincidence that the model Weyl rank over the field K coincides with the...
No, this is not model Weyl.
Okay.
This is the rank of the unit rank.
Okay.
Right. So again, there are tables of number fields that were created since the late 90s. Now you find all of them very easily in the modular database, right? That function in modular forms database. And you look and you classify discriminants by rank, right? So you can say I want to see all the fields that have a certain unit rank of a certain degree, and you can list them by discriminant. This is the first one. And then these two That's first, that's second, for that unique rank, right? And this is the first one in unit rank 3, right? So something special is going on. It's not always going to be the first one, but somehow my problem leads to fields that are very structured and are very, very small discriminant. And I cannot explain that. I'll say a few more things at the end as to what should be explainable, or somebody can try. Right. Okay, so here these fields are not just random. They're actually very, very close to the beginning of the field of a certain discriminant.
So can I ask you a question?
Yes.
So the condition of divisibility, is it equivalent to the geometric condition that if I take the narrow model of E and I look at the end torsion scheme, that splits as n mod n z times mu?
Sorry, I didn't.
Oh, sorry. Is this condition of divisibility of the Tamagawa numbers equivalent to the condition that the group scheme of n torsion on the narrow model V splits as n mod n z times mu n?
I'm not sure that it splits. The narrow model would be, the torsion would be in the connected part. No, I don't know how to, if I have an answer to your question. All right, so to explain what's going on, in a sentence, the field K where there are no divisibilities are very special, right? And to explain very special, I need to remind you of a few definitions. So if you have any ring, an exceptional unit in a ring is a unit R such that 1 minus R is also a unit. And that's a terminology that was created by Nagel in 1969, even though these objects were considered much, much earlier. In fact, that theorem, right, the theorem says that over a number field, there are only finitely many exceptional units. Right? In the theorems that you find in the 70s, might quote Chawla, who in 61 published a very short paper saying, Julia Robinson asked that question, I'm solving it. But in fact, in 1960, independently of Chawla, Sir Lang had a paper on integral points on curves, and he says that theorem follows from Siegel. And then later on, people even say it's already in Siegel. So that's why I put Siegel 1929. But before 1960 or even later, 1969, things had not merged, right? Sometimes mathematics takes time. We're lucky now to have the web and we can search, right? If you had to search in math reviews, these thick books, I'm sure it was not a pleasant thing. Okay, so the next theorem is in 1996. You have an explicit bound for the number of exceptional units, 2 to the power 8 times 1 plus the rank. Right? And as examples, already for Q zeta P plus, you can compute the number of exceptional units, and it grows. Right? These are subsets of units that become hard to deal with as you increase the size of the prime. And that result was already known in 2000 by computations, and now Magma and other programs have implemented the computation of exceptional units, I believe, up to fields of unit rank 10. So 23 is at the limit. I'm not sure you can do Q zeta 29 on Magma, but maybe something has been improved. But somehow we're getting to the limit of what the machine will do for you. And for the quadratic fields, there are only 2 fields that have exceptional units, Q zeta 3 and Q zeta 5 plus. And my next theorem says what I said orally: if you take a number field and an elliptic curve with a k rational point of prime order n, at least 7, such that you're in a situation where you don't have divisibility, then OK must contain an exceptional unit. So I'm going to do much better than this, but this is the flavor. And this explains why these 2 fields appeared in the quadratic case, right? They are the only ones that have exceptional units, so that if you have exceptions, they have to be on that field. Good? All right. All right, so I need to yeah?
There is this
Oops.
theorem, computes again explicitly the exceptional points.
Say it again.
There is this theorem of yours, compute.
So Lenstra came up with this definition. In a ring, you call an exceptional sequence a sequence of elements of the ring. You start with 0, then 1, then U3 up to UM, and you want every difference to be a unit, right? And if you look at the definition of an exceptional unit, this sequence 0, 1, R is exactly saying that R is an exceptional unit, right? So if you want to think about this graphically, if you have a ring, you make a graph where every element of the ring is a vertex, and you link if the difference is a unit, right? And so when you look at that graph, I'm looking for a clique in that graph, a complete subgraph, right? That's what it means to be all. You're going to link every difference in. You have m elements in that graph, and they are all linked. That's called the complete graph. So you're looking for complete subgraphs in the graph of a number field or any ring. All right, so just an easy fact about exceptional sequences. Since the differences are all units, if you do modulo m for some maximal ideals, the sequence injects, right? Because the difference are units, you're not going to go to 0, nothing collapse. So you have an easy upper bound for the maximal length you're ever going to find. It's exactly the length, the smallest norm of a maximal ideal that you can find. Right, and the Lenstra constant is the largest length that you can, larger length of an exceptional sequence. So this was defined by Lenstra in 1977. I think it was in his thesis, and his interest was find things that are Euclidean, but you translate that by now, find fields that have class number 1. So in 1977, high degree number fields were hard to compute the class number of, and he actually found a method where if you could find a long exceptional sequence and in a field that has a small discriminant, small enough, then he was able to say, oh, then you must have class number 1, right? So that was his interest in this. Now, just an example, the Lenstra constant is bounded by by 2 to the d. That's because over 2 you have a prime maximal that has a norm at least at most 2 to the d. But when you look in actual examples, the Lenstra constant is rather small. So for q zeta p, the Lenstra constant is d plus 1, the degree of the field plus 1. And then for q zeta 2p, it's 2d or 2d plus 1. And you rarely go beyond. I think I know one where it's 3d, but it remains really small. All right. So again, so the Lenstra constant is the longest sequence that you can find that is an exceptional sequence. And so the theorem that I can prove is the following. So I remind you that I'm going to refine the theorem that says it has to be contained in an exceptional unit. That says that the Lenstra constant has to be 3 at least. Okay, so we start with like all the other theorems. We suppose we have an elliptic curve with a prime n at least 11, the torsion element of order at least 11, and that we don't have a divisibility. And so if n is 11, the Lenstra constant has to be at least 6. Between 13 and 23, it is at least n minus 1 over 2. And I'm pretty sure that should be the general theorem, but I cannot prove that. I'm stuck between 11 and 23. And then if you go up to 101, there is enough things already computed on the internet that you can get that the Lenstra constant has to be at least 11. And for for all computations that you might be able to do now, this is plenty. Right? So a field should not have any exceptional units, right? That most fields don't. These are really, really structured fields. Right? Okay, so how do we get to that theorem? And in one more step, I told you that if you are in a situation with no divisibility, then the field has to be extremely structured, and in the sense that its Lenstra constant is high. Right? Figuring out the Lenstra constant of a field is difficult. You have to, you have to find a long sequence, and then to know exactly that this is the longest is even worse, right? If you make a machine do it, and it stops doing it after a while. Okay, I just want to point out that this theorem, when the curve has everywhere potentially good reduction, is due to Mestre. And again, in 1981, Mestre was not interested in what I was interested in. He was interested in making examples of Euclidean number fields, right? And he used elliptic curves to find fields that had big Lenstra constant. Okay, so here's a question on the Lenstra constant that I need if I want to go beyond the theorems that I've showed you already. Is it possible to find a low bound C that depends on the degree of the number field, such that you can guarantee that there are only finitely many number fields, k over q of degree d, such that the Lenstra constant is bigger than C? All right. So what's the cutoff on the Lenstra constant? At what point can you guarantee there won't be there will be only finitely many number field with a Lenstra constant that big? And my guess when d is prime is that maybe d is the cutoff. So I'm claiming that maybe when d is prime, like when 7, I'm pretty sure because I can still do computations, there will be only finitely many number field of degree 7 with a Lenstra constant 8 or more. All right, so the application is if you can prove a theorems like this, then the finiteness comes out of this theorem, right? I'm saying here that, I'm repeating the theorem that I just said. If n is between 11 and 23, I'm guaranteeing a high Lenstra constant in my field, bigger than n minus 1 over 2. And if I know that there are only finitely many fields with a Lenstra constant at least d, then I put these two things together, and that gives me n bigger than 2d plus 1. Right? So that's what I had in my hoped for theorem, right? But somehow the finiteness of the number of fields, of the fields that have a high Lenstra constant implies the finiteness of elliptic curves that don't have a cancellation. All right. Okay, so here's the algorithm to find them if you wanted to find them. So I'm going to take the modular curve x1 of n and a very special specific equation for it called the row form equation. That's an equation with coefficient in z. And the theorem is the following. So it should work in general, but I can only make it work for these what is primes so far. Take an elliptic curve with a k rational point of prime order n, such n does not divide, no cancellation. Now, any elliptic curve with a point of order n gives me a point on that row form equation. So I'm calling it R0 S0, right? So that's a point now on the modular curve. I can do that for any one, but I'm going to tell you something about that point. The first thing that I can state is that these numbers R0 and S0 that are going to come out of the raw form equation have to be exceptional units, right? But this is not good enough to get a large Lenstra constant. So let me give you a little bit better, but not yet the full thing. But so I can show that 0, 1, R0, S0, and then R0 minus 1 over S0 minus 1, that has to be an exceptional sequence. And that gives you an algorithm, right? Because you don't care, as soon as you get R0 and S0 to be exceptional units, you can search, because it's a finite set, right? So the algorithm is, pick your favorite field, download the equation that you have for the row form equation, make Magma compute the exceptional units, and search, right? If you find the solution, then you have a curve that I care about. If you don't find any, there are none, right? Good, right? So somehow, for all practical purposes, for small numbers up to 23, you can do it. So I'm going to just end with the case of septic fields, where it's a conjecture because I cannot prove what I want about the Lenstra constant, right? So if I could prove the cutoff for the Lenstra constant, then I would get finiteness here. But I can still search, right? All right, so here's the complete list, I believe, of elliptic curves and fields over which there is an exception, right? So first, it's short. I mean, this is degree 7. There are a lot of degree 7 fields. It's surprisingly short to me, right? And then here, I've tried to indicate where these fields are in the list of fields of that discriminant, right? So this first part here are the fields with one, so this is one unit rank, second unique and third unique rank, and then in the list, this is the first, the fifth, and the 16th, right? I mean, the modular form database has probably 1 million fields of degree 7 already, right? And I'm claiming just this few. And the luck is that you find them at the beginning, right? It turns out that as you move on with the discriminant, you get no more exceptional units, right? So this is the one question, I think, that was pointed out when people were interested in exceptional units due to Lenstra work, but has never been picked up. So this is the number of exceptional units, and this is the discriminant. As you increase the discriminant, there is a clear, in the data, decrease in the limb soup of the exceptional units. But nobody has any intuitive argument or has an explanation for this. So it doesn't go to 0, right? If you fix the unit rank, the number of exceptional units is going to somehow, most of the time it is 0, but when there is a little bit of, there's a threshold where you're going to get infinitely many fields with a little bit of exceptional unit, maybe 126, they will have to be 123, they have to be divided by 6 in general. You could try to find or improve the threshold, infinitely many fields with not that many exceptional units, but to go from there to this threshold, it really goes down. It's striking when you look at tables. There is no exception, no explanation in the literature. So again, conjecture that these are the only cases. You can see that we get into bigger torsions, right? Here we with n equals 7, you can have elliptic curves with a 23 torsion point, and in fact with n equals 7, there are infinitely many elliptic curves with points of order 23. Therefore, this is a non-trivial theorem to say that only these finitely many don't have any cancellations. Do I have another minute, or when?
I think you have 1 more minute.
1 more minute. Okay, so well, okay, I was going to say. No. Okay, so this is all I wanted to say about elliptic curves. Oh, yeah, okay. So we don't know, for instance, what is the largest Lenstra constant of a septic field. It might be stop at 15. I don't know any example of larger Lenstra constant. Okay, so everything that I've asked can be asked for a billion varieties. So for a billion surfaces, the situation over Q is already not quite well understood, because we're not sure what are the orders of torsion of a billion surfaces over Q. So there are a billion surfaces over Q with these torsion orders. but nobody has proven that these were all the possible torsion orders. Over Q zeta 7 plus, that's a cubic field, then you can do 31 and 37. 31 is an example of a curve by a no Melchis, and 37 is a Veil restrictions of a curve that I found of degree 6. You restrict to Veil restriction of degree 2, and you have that. But that's it. These are the known examples over Q of torsion points, right? So already there, we don't know what is the truth in terms of what torsion you can find. Okay, so the situation over Q, that's what I told you. For high order, you can find the divisibility on the nose. You can prove you always have divisibility. And then there is a range where there are exceptions, right? And the question is this the same for a billion surfaces, right? I mean, is that somehow, is there finiteness? So I can prove the divisibility. So if you take an abelian surface with a Q-rational point of order, of prime order n, then for n equals 17 or n bigger than 23, divisibility always, right? So this takes care of that part. High n divisibility. Then there is a range where you could possibly have only finitely many exceptions. So I can prove that there are exceptions for 11, 13, and 19. But I cannot prove that I have them all. And I cannot prove that there are only finitely many, all right? So the known exceptions all have Tamaga number equal to 1. There's a famous one, J1 of 13 is known to have a point of order 19, and the neural model is irreducible. So we get the trivial Tamaga number. N equals 13, there is one parameter family. You search, you find only one in that family, and I don't know how to find other examples. The family of curve of genus 2 with a point of order 13. For 11, we can do a little better. So I just wrote 2 down. One, you find one that is isogenous to J naught of 23. You find one that is a quotient of J167. Broomer sent me one that he had in his table. And then Flynn has a family of curve of hyperelliptic curve of genus 2 with a point of order 11 in Jacobian, and when you search in that family, you find one, and that's it. So I would love if there were finiteness, but for a billion varieties, I don't know where to look for the examples, right? I mean, so I'm not conjecturing finiteness, but maybe. And I'll stop here. Do I know if they are arbitrarily large?
Lenstra constants?
Lenstra constant? No.
Oh, okay.
No.
You know what's the
I mean, I gave you the example of Q zeta p, and that has length the degree or the degree plus 1, I forgot. So if you mean arbitrarily large as you increase the degree of the number field, that's an example where the Lenstra constant goes up. But it goes up linear in the degree of the field. And I don't know more than this. I mean, again, computationally, it's really challenging to actually determine the Lenstra constant if you have to have a sequence of length 15 and guarantee that you can't make a sequence that is longer. You get into large operations that your computer has to do, and I haven't tried. Maybe by now people can, smart people can know how to code correctly, can do something like this. That's an interesting project, actually. But he wants to take it, I'll be glad to help.
What's the difference between the case of n not a prime number?
If n is not a prime number, right? So, right. So The divisibility, so I cannot, I think that there is no good theorem about forcing the points that I said are not S naught, the point on the modular curve, to have coordinates in exceptional units. So somehow, for instance, I only have one example when with a point of order 49 that I computed, and things don't work out as well somehow. You don't get the Lenstra constant that is as big as you hoped you would get, right? It's still, you need something, but it's not as sharp. So.
But the theorem of the divisibility should be true also, or no?
I would have to go look at my notes. No, it's easy to say something and then, no, so with 49, I know that in that examples, the Lenstra constant should be 49 minus 1 over 2, but it's not, it's much smaller, right? So there may be something you can prove about the structure of the field that supports an order of 49 points, but it's not going to be as strong as a prime order point.
Well, apologies if you had done that already in the talk and I missed it, but how do you use now this divisibility or non-divisibility of the Tamagawa numbers to find like fields with new points or?
No, I'm not yet there. These were two different things. Okay. There was question A and question B, and I just made a detour through question A,
okay.
through question B.
Some connection that you...
No, I'm not hiding any connection.
Okay.
All right.
Maybe it was a related question. So, if you assume that, so, are you making a claim that like this R and S in this modular equation, a priori there are M units where M is the conductor, and if N does not divide any of the Tamagawa number, there are actual units? Something like this going on? Like how did you go from like the initial problem of N dividing the Tamagawa number, not dividing any of the Tamagawa numbers, to something about units?
Right. So this is really a computation with. So I have x1 of n with that equation, and I'm going to try to study the narrow model of the Jacobian and see how the points reduces of the elliptic curve. Okay, so I have more. I have when x1 of n with that equation comes with the elliptic fibration, you have the full family on top of it, right? And so I have I have somehow a choice of coordinates that allows me to look at my elliptic curve, and at that elliptic curve, I'm going to say, how does my point of order n reduces in modulo a maximal ideal? And I have to go and actually look at the equations that I get. Right, so my proof is really based on an explicit presentation of the elliptic curves.
Without the divisibility, you know that like each time n does not divide the Tamagawa number, you know that this thing is an m unit.
Each time m does not.
Each time the
right. Yeah, I think what you say is right. Right. I do it one prime at a time.
Okay. And
right.
So they're actual units.
Right.
Not
right. Yeah.